Welcome back, everyone. So we're going to start our session on types and compilers. We have 3 wonderful talks this sessions. And here's Florian Berger talking about same but different. So let's give him a round of applause.
Hello, everyone. As you see, I'm talking about comparative analysis of static type checkers in Erlang. So first of all, why do we even want static type checkers in a dynamic language? Well, and why do we want to compare them? Let's start with a simple motivation or story why we want this. So first we want to implement a static type checker for Erlang. In this case, this is based on the real implementation of Etylizer, which is developed on our university and which will also be part later. Now, what is this static type checker based on? What does it use for types, and how does typing work in Erlang? Well, types in Erlang are defined in the Erlang specs or type specs. Unfortunately, that's quite a complicated document. And we were not sure how to interpret some cases or how to specifically interpret them for our use case. So how can we solve this problem? Well, look at how others solve this problem. Also, if you want to ask why do we actually even want static type checking, well, there are some benefits to it, like we can check a lot of conditions at compile time instead of runtime, but I'm not going into the details of why static type checking is good or not good, so that's a different topic for someone else. Now, looking at some examples of how others solve things, maybe it helps understanding things. So here we can see a very simple function, just returning an atom, and you see all 4 type checkers here say this is fine, no type errors detected. A little bit of a different example, which is still very simple and easy to understand, but here we suddenly already see 3 or 4 type checkers say here's an error, which is indicated by the cross mark, and one says, oh, this is fine. Something to keep in mind for later, maybe. In this example here, we have also 3 type checkers failing, and this time Dialyzer saying this is fine, even though you probably already see that this is maybe not entirely correct or should not be correct. So also interesting result here. And my last example here, a bit of a more complex one, still very simple to be honest, but we'll keep it simple here. We have a custom union type, and there's exactly 1 type checker that even says, oh, there's an error, while the others say this is fine, or in case of Etylizer it says, it's not implemented yet, I cannot evaluate this, which is also important for later, but also not unexpected. Now, with these examples, we already see, even in very simple examples, there are discrepancies between different type checkers. Now the big question is, what kind of discrepancies are there? How many are there, or is there a noticeable number of discrepancies, and why do they occur? Because it should, as we saw, it should all be based on the same set of rules. To find out and answer these questions, we'll follow a few simple steps. We first collect tests for a unified test suite, so we have good data for checking different cases in the language. Then we execute each tool on the same test data. Important, each tool on the entire test data, so we have the exact same foundation for all of them. We convert these results to a unified format, and finally store them for further processing to compare them, visualize them, or do other things with them. What type checkers are we going to compare? Those are the 4 we are using. The first one, Dialyzer, is technically not a type checker, but a static analysis tool. I will refer to it as type checker here because this is the important aspect, although keep in mind it may also report errors that are not technically type errors, but here we will consider all errors of those tools as type errors, which is a bit of an oversimplification, but in general it still turned out to work fine. Gradualizer is a simple static type checker with some support for gradual typing. eqWAlizer is another static type checker developed by WhatsApp, and it's especially based on local analysis, unlike most of the other tools, so it's based on a per function analysis. And it also has a very important property that it reports cases where it cannot prove correctness, which is, by the way, the kind of opposite to what Dialyzer does with its success typing, where Dialyzer only reports definite type errors. And the final one, Etylizer, our own type checker. It's another static type checker, and unlike the others, it's based on set theoretic types, giving it a nice formal and theoretical foundation for the typing evaluation. Now about the test data. What's important for test data to compare type checkers? Here are some of the challenges we noticed and faced. So the first one, exhaustiveness. Test data has to cover all possible cases, or as many as possible. Then there's also the aspect of categorization. How do we decide, is a test something that should succeed or should it fail? Because we somehow need to identify cases that are correct and some that are not. So figuring that out is also an important and sometimes complicated step, depending on the complexity of test cases. Then an important factor here is that we should both have expected fails and passes. There should be test cases that are wrong. There should be some that are correct. And if we already know limitations of tools, it cannot hurt also having test cases that intentionally trigger these limitations. And the last one is not technically a requirement for test data, but more of something to keep in mind when writing or selecting tests. If you write tests and also write your own tool, there will always be bias in some form. If your tool only supports certain features, your tests will probably focus on those features. If you have a certain interpretation of some aspect of the type system, your tests will probably focus on your implementation, but maybe not on the general definition if there's maybe some misunderstanding or something. So that's always important to keep in mind. Now, how do we actually get this test data for the comparison? As we saw, we need sufficient data so we get a meaningful comparison and cover all the important parts. Unfortunately, creating such an extensive test suite is error-prone and very expensive, time expensive or time consuming. You will most likely forget important aspects if you write everything by scratch. Luckily, we already have those 4 type checkers, and each of them has a test suite that is more or less extensive. And so why not just use the test suites of those type checkers? Of course, we need to adapt them a bit, so because some of them use project level tests, others do just single file tests, and we need to get everything into one format so all of them work, which in this case also was per file analysis, because that's what's definitely supported by every type checker, in our comparison at least. And with that, we got this resulting test data set. You see the largest part is from eqWAlizer, and the smallest from Dialyzer. This does not mean that Dialyzer has little tests. The main problem here was that Dialyzer has a lot of tests using non-default configurations, and this always makes comparing things even more difficult, because where do we set the baseline for the tools? Every tool has a different configuration by default, so we decided to take everything with default config, so no custom flags and anything, so we chose to only take the tests that don't expect custom flags for Dialyzer. Of course, this is also not a perfect approach, but it's the best compromise here that's possible. So, also Dialyzer was the only test suite where we dropped a really noticeable amount of tests. With that, let's have a look over some of the results. These are the overall results of all the type checkers on the entire test data. You see overall, eqWAlizer has apparently the best result, while Etylizer has the lowest passes. And also you probably notice on Etylizer the big not implemented chunk, but let's have a closer look in detail, because you saw the test suites have different sizes, and also maybe the test suite has effects on its or maybe type checkers behave different on different test suits. So let's get into the specific test suits for better details. All right, these are the results for all the tools on the Dialyzer tests. Those are the 73 tests I mentioned before. Initial observation is that tools appear to perform best on their own test suite. As you see here, Dialyzer has no errors at all. But this is still an initial observation. Of course, we have to look at the other test suites to confirm this. And we also see that Etylizer had those not implemented test cases. Also, you probably know Etylizer has a very low number of actual hard fails, but those not implemented cases cause the results to look a lot different. And overall, we also have something we call diverging results, which are results where one type checker came to a different, or at least one type checker came to a different conclusion than the rest. In this case, there were 54.8% of all the test cases in this one with diverging results. Those diverging results do not include not implemented results or other unknown errors, timeouts, and crashes, because that's not really meaningful for that result. Let's get to the second test suite, the eqWAlizer test suite. We confirm our observation from the previous slide. eqWAlizer is also the best on its own test suite. It does have some fails, unlike Dialyzer, but still very little. And Etylizer has again, little hard fails, but a large chunk of not implemented errors. Also, considering that these are more than 1,000 tests and a large chunk of the overall results, this probably also gives a bit of an idea why maybe eqWAlizer performs so well overall. In this test suite, we had about 43.5% of diverging results, which is lower than before, although this low sample size from the previous test suite may also skew things a bit. For the Etylizer test suite, things look pretty much the same as expected. At first glance, Etylizer doesn't look like it performs best, but if we ignore the timeouts and memory problems and the not implemented cases, it has the least number of hard fails here. Slides are a bit slow. Yeah, as you can see here, it has, of course, on its own test suite, it has very few not implemented test cases, as is probably expected. And we also notice those timeouts and memory exceptions. Those are basically cases where it gets stuck on something and exceeds memory limits we set in the comparison. Again, on this test suite, we have roughly 42.5% diverging results, which is in line with the previous results. And finally, the Gradualizer test suite. Again, no real surprises here. The previous observations have been mostly confirmed. We again see it performs best on its own suite with a noticeable amount of fails, but also still the least fails. Etylizer is technically about on the same level of hard fails, but the many not implemented cases and memory and timeout errors push it down a bit. And on this suite, we have again 56.5% diverging results, which is higher than the previous ones, but still within the previous margins. So, to summarize those observations, we noticed that there are significant differences in accuracy between each tools, on the overall test suite and on the individual test suites as well. Each tool performs best on its own suite, and Etylizer was the only one that had timeouts or exceeded the memory limit. However, this is not something that should be a negative aspect in general, because it's also the only tool, as far as I'm aware, in this comparison that is not fully implemented yet. So this is to be expected. As we saw, eqWAlizer was the most accurate type checker. And we also noticed that many of the errors of eqWAlizer are caused by intentional limitations of the implementation, which I'll cover in the next slides in more detail. Also, there was this disagreement between the type checkers in about half the test cases overall, and a very little number of flaky tests which were so low that it's not really relevant for the overall results here. Now, let's get back to our initial questions, why we even wanted to do this comparison. How many discrepancies are there? Well, as we mentioned, that overall diverging results, those are the discrepancies that we mentioned. In total, 1,019 test cases, which is a bit less than half of the total test cases, which is kind of high, to be honest. And there were 354 cases where exactly one type checker disagreed with the rest. These are maybe the more interesting ones to look at in closer detail, because if only one type checker disagrees, this may indicate some issue either with the implementation of that one type checker or maybe the interpretation of the type language of that type checker. Now, before I mentioned that Dialyzer is not a type checker but a static analyzer, so if we remove Dialyzer from the equation, we still get roughly the same results, although now we get only a third of the tests with disagreement. But keep in mind, we also removed 1/4 of all the results that were used for the checking for disagreements before, so it is to be expected that the number is lower now.
Excuse me. So here you have 3 type checkers. How can you have 763 test cases where they don't all agree, but only 297 where one disagrees with the other 2?
It's a bit skewed because of the not implemented results. That was a bit of a... Yeah, it's not entirely clear, sorry. I should have mentioned that. In this number, I included them because obviously otherwise it would be relatively easy to already see the difference. It wouldn't be necessary to point out that specific one.
Can I ask another clarifying question? You said just 2 slides ago that one type checker is more accurate than the others. What does accurate mean?
Let me come back to that later, maybe, no? And I'll answer it after the presentation slides, if it's still not answered then, if it's fine for you. Okay, so what discrepancies are we talking about here? This is this is a list that covers the most important ones. It cannot cover every single one we noticed, because then I could fill 10 slides and be here tomorrow. But overall, eqWAlizer fails to detect type errors related to numeric types, which is something to keep in mind. It also fails to detect exhaustiveness issues in many cases, which is also a problem of some of the other type checkers. Not all, and in some cases some work, then again in others they don't suddenly. For Etylizer, obviously the not implemented cases are causing some discrepancies, because it's not fully implemented yet, so in the disagreements we excluded it in most of them. And also in Etylizer, specifically there was no support for type variables, especially in maps, because it's not supported in the set theoretic framework as far as I'm aware yet. But this is something that's considered not implemented yet, so it's less of a big issue, or not really a big issue here. And in general, we noticed exhaustiveness checks appear to be difficult. There are the simple cases where it's just a basic with 2 or 3 cases. Most of them work fine, but if we get into union types and more complex structures, it becomes difficult for a lot of the type checkers, and none of them was perfect in that at all. Then, now that we know how many and what discrepancies, the final of our 3 questions: why do these occur? Some of them are by design. So, for example, eqWAlizer does not differentiate between different numeric types. An integer, and a float, and also singleton numerics like 42, 43, they are all the same for eqWAlizer. Apparently, it's just not a use case they had, so it was omitted by design and is something to keep in mind here. It also doesn't support exhaustiveness in most cases, except for very basic ones, which, according to the developers, is also by design. then default configurations caused some differences, especially with Dialyzer it was very noticeable, because Dialyzer will not report a lot of stuff like underspecs by default, or will just report some cases as warnings, but not as errors. And unfortunately, our analysis only focused on errors, because detecting warnings would require parsing the entire standard output, which can become quite difficult if you have to check for dozens of possible patterns. And the last one, which is more of a problem of the test suite or the test suits from the tools, are that some tests were not properly categorized. We're not sure why that is the case, but maybe those are leftovers from before. We cannot really answer that because we did not write the tests ourselves. And the last one, especially for some of the more complex aspects like type variables and maps and stuff, there are some discrepancies apparently in the type specification where it's not entirely clear how to interpret it and how to implement it, but that's just a separate thing from the more obvious parts. With that, we are at the conclusion. So, as you saw, there are discrepancies between type checkers. Whether they are caused by the implementation of the type checker or maybe by type specification, some of those discrepancies are intentional. Others could indicate those issues I mentioned in the definition of the typed language or the spec of the language itself. And this unified test suite provided a very good starting point for this comparison. However, there is more work needed to turn this into a truly representative test suite, especially considering that tools have different default configurations and everything, and also different supported feature sets. And this could also turn out as potential for further collaboration between tools to work together and create this, well, proper representative test suite where also the specifics of each tool are considered to get a really good comparison. Thank you very much.
Can I ask my question again?
Yes.
So I guess another way to frame it is a test suite is usually saying, does a program meet its specification? So is there a specification for what it means for an Erlang program to be type correct? Other than, I suppose, programs that pass the analyzer should not go wrong for some meaning, some version of go wrong at runtime?
Well, there is a specification in the Erlang language specification. As I mentioned before, there are type specifications for typing in Erlang. But that's also the problem here, the interpretation of the spec. I mean, there is the spec that is, there's the formal spec you have in the language, but does it really cover all edge cases? And that's also one of the topics here that I mentioned here, having a critical evaluation of this type language and the spec itself, because that could maybe also be the problem here. So that's something not 100% clear if there's a perfect specific definition, or if maybe there are some things that are not that well defined.
So perhaps you're saying that your work gives a series of suggestions for how to make the specification tighter. It identifies weaknesses in the specification.
Exactly.
Is that right?
Yeah, basically we provide the starting point where we identify those potential weaknesses or discrepancies where something is not that well defined.
Okay.
So as part of that, Florian is not so much involved in that, so he doesn't know the details, but we've been starting to have more proposals for changing the Erlang language or Erlang type language specification, because it turned out, like, for example, the type variables are very difficult to interpret, and the specification very clearly says how they are supposed to be interpreted, but even the standard library annotations and what programmers use is diverging from it. Yeah, so you have some of the type checkers doing what the programmers intend, and some of them following what the language specification says. And this is exactly one of the reasons why we started doing that work, because yeah, that's something we need to fix as a community. I guess Kiko also wants to say something on that.
Yeah, so the problem in this case with generics is that type variables are interpreted as values, So if you say X, you mean exactly this value that you plug into the type, not the type. So the interpretation was based on success typing, and that's why no one fully understood it. So even though it is written, everything is written as if we have generics, but we never had. And that is one of the main issues that we're trying to solve, in this case, over time. Yeah.
So you talked about cases in which type checkers pass and fail. But thinking about it, there are two ways in which a type checker might fail. It might reject a program that you think it should have accepted, or it might accept a program that you think it should have rejected. And I have a feeling that one might regard those two kinds of failure as different in seriousness. Can you say anything about which happens most often?
What was the last sentence?
I just wonder if you can break down your results in any more detail to these two different kinds of failure.
I'm afraid I don't have the full detailed analysis here. We do have the results that we can break down. Albert also wants to say something, but in general, I don't have the completely detailed results here, but in general, we categorize the fail as both the cases you mentioned. In the paper, we looked a bit closer into it, but it was not the main focus here, to be honest. Also,
I can say something about this. So what you're talking about are false positives and false negatives. Dialyzer has no false negatives. That's also the goal of the tool. That's also a big positive. Gradualizer has a lot of false positives, so a lot of noise. That's just because the limitation of the underlying algorithm. It's not able to type check a lot of, for example, intersection types and so on and so forth. So it's just a limitation of the tool itself. eqWAlizer has not a lot of false positives on its own test suite because it's expected, but a lot of false positives on other test suites where, for example, these numeric types are used as they are intended. So it will produce a lot of noise where you use the tool with not its intended design. And what have I forgot? Etylizer is also trying to have a lot of less false positives because we try to have a very expressive language to capture all the intended use case of the language. So we try to work on all code bases, but as you see, it's harder to capture everything.
I'm sitting in front of the author of Quick Check, and I was expecting to hear you say, these things come with a pitiful 100, 200,000 test cases. We would use Quick Check to generate 100,000 test cases. Now, why is that difficult usually for a type checker? It's because we don't know what the answer should be if we generate 100,000 test cases. But here, you can use each of the checkers as an oracle for the others and say we generated 100,000 cases and they differed on, 5% or 50%. And then you could use shrinking to find the smallest example that would distinguish between. That would be such a cool thing to do, given that you have them all as an oracle for the others. Maybe it's just an idea for future work, right? I'm just sort of, John is kind of doing a sort of puppet thing behind my head.
I think that's all the time we have for the session, so we'll take the rest of the discussion offline. Thank you, everyone. Thank you, Florian.